Good evening to all. Today we are going to explore a software for polarimetric SAR data processing. So in today's session, we are going to explore Sentinel application platform Snap software for the polarimetric processing of SAR data. And the data set is taken here, radar set 2 C-band SAR data set for Vancouver area. And the dataset and software both are freely available because this dataset is sample dataset. So you can explore this link to download the data, and the Snap software is available on the link maintained by European Space Agency (ESA). So using both, one can download the software as well as the dataset. Now the dataset has also been kept at the IRS FTP link. So here ftp.irs.gov.in, if you will have internet access, so differently you can get the data set. And if you will use this FTP, so it is going to ask user ID and password. So username and password both are written here. And like for each and every course, there will be different user ID and password. So particularly for this course, the username and password is given, so one can use it to download the data set. And if one is interested to explore other softwares, so this is list of open source softwares. One can go through the software's link and they can download it and they can do the data processing. Now we are going to open Snap software to process radar set 2 data set. When you will open the software, you are going to get this link. So you can get different tabs like file, edit, view, analysis, layer, vector, raster, optical, radar, tools, window. So our main interest is radar tool. So in radar tool, if you will see, there are several options like radiometric calibration, then speckle filtering, then co-registration, then interferometry, polarimetry, geometric operations for terrain correction, which we had seen in the last lecture, importance of terrain correction. Then Sentinel-1 TOPS processing, then InVSAT SR processing. Then there are different other applications also, like if you will see the SAR applications. So in SAR applications, if there are several themes, one is ocean application. So here in ocean application, one can work with ocean object detection. So this is particularly for ship detection or any other object detection in the ship. And another tool is there for the oil spill detection. And the third is for wind field estimation. Now, if you'll go to the urban area, so spectral divergence based approaches are given to detect urban area. And similarly, there are several other approaches like multi-looking and complex to ground rays. So these tools may be used to process the SAR data set. Now, if you'll go to the window, so if one will be able, is interested to generate RGB view of the data set. So from here, one can find out the RGB view of the data set also. Now we are going to, like before doing any processing, so first we will have to import the data set. So now we are going to import the data set. So to import the data set, we will have to click on File menu. In the File menu, we are getting here you can get the open product, reopen product. So first of all, we will have to import the data set. So when you click on import, you are going to get several options like DEM, generic file formats. If your data set is in GeoTIFF or INVI file format, so you can directly import those formats. And this software is capable to process optical data sets also, optical multispectral data sets. So this option is also given. But here, if you go in the SAR format, so there is compatibility given with the Gamma software, then PolSAR Pro software, then RAT software, then generic complex, and the generic binary format could also be read by this software. Now, our interest is to import the radar set 2 data set, because 1 QoR area sample data set is provided by radar set 2. So that data set we are going to open. So now if you click on the SAR sensor, so here you are going to get several satellite option for to import the different satellites, like ALOS Pulsar 1, then ALOS 2, Cosmos SkyMed, then similarly ERS1, ERS2, JRS, ComSat, Radar Set 1, and Radar Set 2. Now, if you are processing the sample data sets or the Sentinel-1 data sets of your study area, so this software can be used to process Sentinel-1 data set, TerraSARX, TandemX, and the several other file formats also. So now we are going to import Radar Set 2 data. So we are going to import the Radar Set 2 data. So I have clicked on Radar Set 2. Now after that, this view will appear, this window will appear, and here we will have to give the input of the data set. So this data set is kept on desktop in 42nd course folder, and here I have there is another folder with the name data, and data set is kept here in RS2 OK76385 folder. Basically this is the name of the data, and I have created another folder to save the output file. So snap output folder is also created. So one should create this folder, otherwise it will go to the default folder according to their setting. So I am just going to open the data set. Now before opening the data set, I will have to open this folder. So in this folder, the software is not directly going to read the data set, because if you will see in the desktop, if you will see in the desktop, when I am going to open 42nd folder, so here the data set is having the 4 polarimetric channels, HH, HV, VH, and VV. So these four polarimetric channels will be available, but softwares are not directly going to read these polarimetric channels. They are going to read the product.xml file. So here in this case also, software is going to read product.xml file to open the radar set 2 data, because software is not going to directly read the original data, main data. This is going to read the metadata file. So the product.xml file is the metadata file. So I am going to open this product. Just simply click on the product and product.xml file, and again after that click on import product. Here you will get one option, if you'll see the cursor, to import product. So I am just going to click import product. Now after importing the product, you are going to get the product in the product explorer. When you will expand the product explorer, you are going to get several other information, like the first option is of the metadata. So when you will see the metadata, so abstracted metadata and the original product metadata, all the things are available. So when you will double click it, metadata will be appear, and here you can see that procurement time was 10th May 2016. Product name is radar set 2 RS2 SLC. SLC, this is representing the single look complex data, and the mode was fine quad polarization mode, and beam number was Q2 according to different angle of incidences. Number of beams were defined. So this is beam number Q2. For beam number Q2, incidence angle in near range is 19.78 degree, and far range incidence angle is 21.8 degree. Okay, so accordingly, and we can get the coordinate information also, and different information of polarimetric channels are also given. And here this is given the range spacing and the azimuth spacing. So here this is given the range resolution is 4.73 meter, azimuth resolution is given 4.87 meter. Now again, when it will be when one is going to minimize slant to ground range ambiguity, so this range spacing should be divided by sine of mean angle of incidence. So mean angle of incidence will be approximately in between 20 degrees. So this will be divided by sine 20 degree, and whatever the values will be there. So accordingly, number of looks will be calculated. And there are several other information. If one is interested, they can go in detail of all the information available with this data. Now, when we are going to see the tie point grid, so here we are going to get the latitude, longitude information, angle of incidence information, and slant range time. So like with SAR data set, when the SAR data set is provided, so this information of latitude, longitude, angle of incidence, and slant range time. Actually, slant range time is the time taken by the electromagnetic wave for the two-way propagation to track the target. Like this is the time which is taken by the electromagnetic wave from sensor to the target, and after scattering, target to the sensor. So there is two-way propagation time. So when we will multiply this time with a speed of light and divide by 2, so you are going to get the range distance, the distance between target to the sensor. uh, this information could be collected, and this range distance is going to vary from near range to far range, because time taken by the electromagnetic wave to track the target in near range and far range both will be different. Okay, now after that we are going to explore the bands. So if you will see these bands, so bands are IHH, QHH, then intensity HH. Similarly, the information is there for different all the remaining polarimetric channels like HV, VH, and VV. Now, when you will see the IHH, so IHH is representing real channel or in phase component of horizontal polarization. Like HH means horizontally polarized electromagnetic waves were transmitted and horizontally polarized electromagnetic waves were received. So I is representing real channel information of the HH polarization. Q is representing the imaginary channel information of the HH polarization. Now software is capable to create an intensity image virtually in the memory. So here you can see that intensity HH is there, but you are getting the symbol V, means this is created virtually. Similarly, for all the other remaining um, polarimetric channels like HV, VH, and VV, you are going to get the information of real channel, imaginary channel, as well as the intensity information. Now, if one is interested, we can visualize the IHH. So this is going to take some time to open the polarimetric channel. So here one can see this is IHH. Now in IHH the things are not clearly visible, because when you separately visualize the features in real and imaginary channel, so we are not going to visualize any object. If you know the area, then you can move the cursor in the navigation menu. There will be one zoomed window, so accordingly you can zoom the data set and you can visualize the object. Similarly, I am going to open another channel, imaginary channel. This is Q. Both are appearing similar and they will have the values. And similarly, I'm going to see the intensity image. Now some information is there in intensity image. If you zoom it, you are going to get the different type of features in the study area. Okay. Now we are going to see the main question is like how to see the values. So if you click on the pixel information, suppose you are clicking on the pixel information, so you will be able to see the real and imaginary channel values, not only I and Q, but their intensity values also for different location. You can see that for different locations values are ranging. Okay, and if one is interested to see the angle of incidence time, it means that the angle by which the electromagnetic wave were interacted with the target. So those angle of incidence information is also possible to see. Okay, suppose I am zooming it. If you'll simply zoom in or zoom out, you can get the info. Suppose particularly for this pixel. Okay, so if you'll expand the tie point grids, so you are going to get the information of Q means real channel, imaginary channel, latitude, longitude, incidence angle, like particularly for this location, angle of incidence is 21.36 degree, and slant range time is 5674208 nanosecond. Now, when you multiply this nanosecond with the speed of light divided by 2, then you will get the total distance in meters or kilometers, whatever unit you are selecting. Okay, and if one is interested to see the value of the resolution cell in different pixels, so differently they can see. Simply they will have to open other polarimetric channels also. If all the polarimetric channels will be open, so one will be able to see the information of scattering by one resolution cell or by one feature in different polarimetric channels. So here you can see in different polarimetric channels, their values are different. Okay. So now one can explore these things. There are several other tools also, so one can go and explore in the software. Now we are going to start the processing of the SAR data set. So first, we are going to see the product explorer. We are going to just minimize the expansion. And as we know that first step in SAR data processing, we are going to do the slant to ground range ambiguity removal and multi-looking. So this multi-looking operator is going to minimize slant to ground range ambiguity by multiplying the slant range by 1 divided by sine of angle of incidence or look angle. So this will be calculate the slant range will be converted in the ground range, and finally square pixels will be generated by calculating the number of looks in azimuth and range direction. So here when you will click the multi-looking operator, so you are going to get this window, and here we will have to give the input. So input is our data set, and you can fix the output. So here I have fixed the output in this folder, snap underscore output folder I had created on desktop. So what will happen after processing, all the output, or the result will be saved in this folder. Now after that, I am going to click on the tab processing parameters. When you are going to see the processing parameters, so you are going to see all the polarimetric channels which were imported from the data set are available here. If one is interested to process particular polarimetric combination like HH or HV, then they can select, or they can select all, or if they are interested like all the processing should be done for all the polarimetric channels or all the combination. So if you're not going to select any particular polarimetric combination, so by default the processing will be done for all the polarimetric combinations. Now number of looks is automatically calculated. So in range direction, number of looks is 1, and in azimuth direction, number of looks are 3 to create a square pixel of size 13.96. If one is interested to calculate the number of looks according to their own calculation, if they are not satisfied with the values given by the software, because software has calculated according to metadata, if they are doing their own calculation, and if they want to change an independent, if they want to change the number of looks, so they can click on independent number of looks, and it will be done according to their independent parameters, according to the user provided number of looks in range and azimuth direction. So here I am going to click the default value. So by default, it has calculated 1 and 3. Now I'm just going to click on run. So it is asking because in the morning session I had just tested. So the file is already available with the name underscore ml dot dim format, because in the morning I had just tested, so that I have done this processing for multi-looking. So the software is asking, do you want to overwrite the existing file? So I'm just going to click yes. So now processing has been done, and you can get the information like processing completed in 1 second, whatever the time will be taken. It is there. Okay, now I am going to close this window. Now the data set is multi-looked. So when the multi-looking was done, so according to the size of the data set, the software has automatically calculated the same size of the incidence angle file and slant range time file also. If you will see, if I will move the cursor, you can see the angle of incidence file and slant range time. Both the files are calculated according to the size of the data set. Now, I am just going to explore to see one band. So suppose I am going to see the intensity.hh band. So here you can see the intensity band of HH. We are able to see the information of different targets, linear, non-linear features. Okay. So in the next step, we are going to do the steps for the radiometric calibration, because here you can see in the intensity and the real and imaginary channel information, values are ranging, or like here you can see values are ranging like -1, particularly for this pixel. The IHH is 1580, QHH in the Q imaginary channel, the value is 544 earlier. Similarly, like particularly for this pixel, 1298, 712, and its intensity will be your I square plus Q square. So values will be 21, 91, 748. So this range is really very, very high. Now there is a requirement, because this is depending on the sensor characteristic, like how much range could be acquired or collected by the SAR sensor. Now we are going to do the radiometric normalization. Now, why the radiometric normalization is required? Because in the radiometric normalization or the radiometric calibration, with the help of the formula provided by this speciency, like in the last lecture, we had seen the formula for TerraSAR X as well as for RISAT1, because for different satellites, the formula will be provided, different formula will be provided, or if one wants to use a standard formula, so a standard formula is also there, which will use the sensor parameter as well as the object parameter. Now, here in this case, we are going to do the radiometric calibration of the SAR dataset. Why? Because there is requirement to provide a common platform to the SAR dataset, because otherwise the values are going to have several high and low ranges. Now, after calibration, the values will be at linear scale. They will be ranging from 0 to 1. So that I am going to do the radiometric calibration. After that, we will see what values we are getting after radiometric calibration. So if you go to the radar tool tab, so there will be another tab like radiometric, and in radiometric we are getting the option for source product. Click on source product. Our input, when you will give the input to the first product, so the first data set will be calibrated. Then again there will be requirement of multi-looking. Now here I am going to select the input as multi-look data set. Otherwise, again I will have to do the multi-looking after calibration. So first step I am going to give, the source product I am going to give the multi-look data. multi-loop data is represented by underscore ml. Now you can see, like, for each and every processing step, after the output name will be added according to the step. Like here, previously, in the product explorer, if you will see, the output name has been added, like multi-loop data set was generated with the name underscore ml. Ml is representing multi-loop. Now I am going to do the radiometric calibration of the multi-loop dataset. So after ML, there will be another underscore and the CAL. This is representing the calibrated data. So the calibrated dataset will have the name or the original name of the file, and underscore ML and underscore CAL. Now again, I'm going to click on the processing parameters tab. In processing parameters tab, if one is interested to do the polarimetric processing of the SAR dataset, then the SAR dataset should be represented in the complex format. If it will be converted into intensity, then polarimetry will not be possible. So if you will select any, like here we had talked about three different calibration constant: sigma naught, gamma naught, and beta naught. Now save as complex option we will have to select. Why? Because the first option will generate, the second option, which is save in dB, is going to generate sigma naught image at dB scale. This will be gamma naught image, and the beta, and the last one, fourth one, is the beta naught image. So our option is save as complex output, so that the calculation of radiometric normalization will be done on I and Q, both the channels, independently, so that the data set will be radiometrically calibrated, and it will have the complex information also. When you will selecting any other option, so the data set will be converted in the backscatter image through intensity or amplitude. So it will be very difficult to do the polarimetry, but practically, like particularly, it will not be possible, because here you have seen, like, to generate the coherency matrix or the poly RGB, there is a requirement that the data set should be in the complex format. Like when you are generating the coherency matrix, so your poly feature vector should be multiplied with its own transconjugate. Okay, so to do these operations, the data set should be in the complex file format. If you will have any confusion in generation of the coherency matrix and other parameters, then I would like to suggest you to do the revision of the previous lectures on SAR polarimetry and the SAR data processing. Now again, the output will be saved in the snap underscore output folder, and after setting these parameters, I am going to click on run. Now the processing has been done, and we are going to get a folder, output with the name underscore ml and cal. Now if you will see the ranges of these values, so you are going to get, like in the case of intensity, if you will see the intensity value, so this is going to range from 0 to 1, and for I and Q values, these are going to range from -1 to +1. So that intensity will be ranging from 0 to 1. So here you can see now the values are ranging from -1 to +1 in real and imaginary channel, and in intensity 0 to 1 after radiometric calibration. Okay. Now if one is interested, they can generate the I think, okay, these values has been they can simply generate the RGB view of the data set. If you click on the window, so this from here, open RGB view one be clicked, and one can generate the RGB view like poly and Sinclair, and there are several other modes of dual polarimetric data sets are also given. And if you want to save that RGB, so simply you will have to click on store RGB, so that the RGB will be added here as channel. Suppose I'm going to click the store RGB for the poly, so it will be added here. Now I'm going to click. If you'll compare, the formula is similar. The formula for the poly decomposition or poly feature vector, the formula which you had seen during the class of polarimetric, basic concept of polarimetrics are remote sensing. So the formula is same, and here I'm just going to click, and if you generate, this is the poly RGB generated. Now very much clarity is there. If you will see, like entire water body is represented by blue color because first element of poly feature vector is HH plus VV. So HH plus VV is represented by blue color, and second element is HH minus VV, and that is sensitive for the double bounce scattering, represented by red color. And the fourth element is HV, that is sensitive to the volume scattering from vegetation, represented by green color here. So here you can see that the things are appearing according to their scattering values. Okay, and if one is interested to convert this virtual band into the real band, so simply you will have to click the cursor there, then right click there, and if you'll click on convert to band, so this will be converted to the band. Okay, now after that we are going for the polarimetric processing. Okay, so if you'll click on radar, so radiometric calibration we have performed, multi-looking also we have performed. Now there is option for the speckle filtering. So currently if you will go for the speckle filtering using this tool, so the data set will be converted into the intensity file format. So it is not good. We will have to do the, if one is interested to do the speckle filtering of the polarimetric SAR data set. So the speckle filters for PolSAR data sets are of different category. Either they will be implemented on the complex channels, or they will be implemented on the coherency or the covariance matrix. So first we will have to derive the parameters or elements of the polarimetric matrix. So there is one option to launch PolSAR Pro. So currently the PolSAR Pro software is not available because latest version, they are going to release the latest version, because PolSAR Pro is the currently we can say that PolSAR Pro is the strongest software to process the polarimetric data set, to do the polarimetric processing of the SAR data set. But one will have to use both the softwares, Snap and PolSAR Pro, if they want to use the Windows-based software to do the complete processing of the SAR data set, because like PolSAR Pro cannot do the georeferencing or the ortho rectification, but those things could be easily done in Snap. So if one is using PolSAR Pro, so again they will have to import the data set from PolSAR Pro to the Snap file format to do the georeferencing. Okay, now I am going to do the polarimetric matrix generation, steps for the polarimetric matrix generation. So I have clicked here, and make surety about your source product. So here our source product should be multi-looked calibrated SAR data. So this product, I am going to check it here. I am going to select the product multi-looked underscore CAL, means calibrated, multi-looked calibrated product. Now when the multi-look calibrated product has been selected, so I will have to go and see the processing parameters. So I am clicking the tab processing parameters. Now in processing parameters, it is given the polarimetric matrix T3. Okay, if you simply expand it, you are going to get C2, C3, C4, T3, T4. Okay, so C2 is the matrix, covariance matrix generated for dual pole SAR data set. C3 is generated for quad pole data set acquired by monostatic SAR system. Okay, because in the case of monostatic SAR system, the HV, that means both the cross polarimetric channels will be similar. Okay, HV should be equals to VH. Okay, so at that time one should go C3. If they are using the bistatic SAR data set, then one can go for the C4 also, because in that case in bistatic VH will not be exactly equals to HV. C3 is representing covariance matrix, T3 is representing coherency matrix. So now we are going to explore, going to generate coherency matrix T3. One can generate C3 also, but currently we are going to move with T3. Now I am going to generate T3 after checking input and output parameters and their path. I am going to click on run. So again, the processing has been completed in 1 second only. Now you can see here the name is ml underscore cal underscore mat. Suppose if you are going to forget any step and you are thinking that whether you have processed that step or not, or that has been simply done by you or not, so that could be easily checked here, because for each and every processing, steps will be given accordingly. So here in this output, it is showing that the first step was multi-looking, the second step was calibration, and third step was polarimetric matrix generation. Okay, so here we are going to see the different elements like T11, T22, and T33 we have seen during our classes of basics of PolSAR remote sensing. So we are going to just explore T11, T22, and T33. So these three elements we are able to see. If one is interested to compare, they can compare it, or if anyone is interested to generate RGB view, so here by default this is giving T11 as red, T22 as green, T33 as blue. But here we know that T11 is very much sensitive for surface scattering. So surface scattering is always represented by blue color. So that here we are going to select T11. Okay, and in the case of green, T22 has been selected, so this is okay. In the case of red, in the case of actually T33 is sensitive for the volume scattering, so here we will have to select T33, and red is represented for double bounce scattering, so we are going to select T22 there. Okay, so red, in the red we had selected T22, in green we had selected T33, means third diagonal element of coherency matrix, and in blue we are representing blue like your surface scattering, or first diagonal element of coherency matrix is represented by blue color. So again, I'm going to generate color composite, so we are going to get similar type of information as it was there in the poly decomposition. If you are thinking that okay, there is requirement of speckle filtering, so one can go for the speckle filtering also. So simply they will have to again click on radar tab, and they will have to go to the polarimetric, and here we are going to get speckle filtering, polarimetric speckle filter. Okay, so suppose I want to do the polarimetric speckle filtering, so I can click on polarimetric speckle filtering. I am going to get this window. Again, I will have to check my input. So input is multi-looked, calibrated, polarimetric matrix generated data set, and there will be speckle filtering with the name underscore SPK after all the processes. So HS plus VB is represented by blue color, and second element. Now the again, I am going to check the processing parameters. So if you go to the processing parameters, so there are different speckle filters given here, like refined leaf filter, boxcar filter, IDN filter, then improved Lee sigma filter. So I'm going to select boxcar filter. If you will explore PolSAR Pro, so you are going to get more filters. But since the software is capable to do all the processing at one platform, so that I had selected this software. So boxcar filtering I am going to select, and have given the filter size of 5 by 5. And my output will be again in the snap underscore output folder. I'm going to click on run. So again, processing is completed, and I just want to explore the product. So before that, I am going to close all the open window. Otherwise, what will happen? This will consume the memory of the system. So again, we can see there is T11, T22, and 333. Now after that, I am going to open the RGB view just to see whether is there any enhancement after speckle filtering or not. So red is represented by T22, T33, and T11. Okay, so I am going to no. I have not opened the speckle filtered product. Our speckle filtered product is here. Yes. Now after speckle filtering, you can see in like T11. This is the T11 before speckle filtering. First element of first element of the coherency matrix, and this is after speckle filtering. You can see that lot of enhancement is there. Now I am going to generate color composite using this data set. So click on window, then open RGB. Again, we will have to select here red will be represented by second diagonal element of coherency matrix. Green will be represented by third diagonal element of the coherency matrix. Blue should be represented by the first diagonal element. Now I am going to generate RGB. So here you can see better visualization in the terms of radiometric enhancement is there after doing the speckle filtering. And here you can see some small ships are also visible in the sea. So here you can see the scattering pattern, and like agriculture lands are also visible. If you can see at the center, uh, you can zoom it and you can see the information. Now they are showing the scattering information according to their characteristic target feature and interaction with the electromagnetic wave. Accordingly, we are going to get the different type of scattering like volume scattering, surface scattering, and double bounce scattering. We are getting the pattern according to the shape, size, and structure, as well as the electrical property of the object. Now we are going to move for the uh, incoherent decomposition modeling approaches like Freeman and Yamaguchi. So we can see those polarimetric modeling approaches. So these are here. If you'll see, there is one option for the polarimetric decomposition. So click on polarimetric decomposition, and here our input should be the speckle filtered output, and target name will be underscore decomposition. Now if you'll see the processing parameter, so it is asking which decomposition you want to implement: Sinclair decomposition, poly, Freeman-Darden, generalized Freeman-Darden, Yamaguchi, Van Zyl, cloudy, or HA alpha quad pole decomposition. So you are free to select any decomposition model based on the characteristics of the type of the modeling approaches. Like if one wants to select a decomposition model based on the characteristic of the characteristic as we have discussed, like coherent and incoherent. So coherent and incoherent decomposition, when we are talking, so Sinclair and the poly decomposition, these are a type of coherent decomposition model. And Freeman-Darden, then Yamaguchi, Van Zyl, cloudy, and HA alpha decompositions are the type of incoherent decomposition models. So if they want to compare the decomposition model based on the coherent and incoherent, so they can select Sinclair and poly decomposition. If they want to select any incoherent, so they can select any incoherent decomposition models. Again, when we are going like after coherent and incoherent, in incoherent also, if one is going, incoherent decomposition models are basically derived based on the coherency matrix element, 3x3 coherency matrix element. So again, these like Freeman, Darden, and Yamaguchi, Van Zyl decomposition, these are based on the model-based decomposition after decomposing the coherency matrix element. And when you will go to the HA alpha decomposition, HA alpha decomposition is the decomposition based on the eigenvalue and the eigenvector. And this decomposition will this has been done based on the role invariant parameters. So there are different techniques to select a decomposition model. One can go in detail to find a suitable decomposition modeling according to their choice. And in each and every type, there are several decomposition modeling approaches, so they can go and see. Now suppose I am selecting the Freeman data and decomposition model. So one can click on Freeman data and decomposition model. Here I am going to select window size 1 because I have already done the smoothing with the help of 5 by 5 window. Again, if I will select the window size 5, so again it will do the boxcar filtering in the background. So again there will be two level of filtering. That is not always good because I have already done one filtering. So I have selected window size 1. So in the background it is not going to do any filtering. Now after that, after selecting Freeman data, I am going to click on run. So simply click on run so that the modeling will be done and we are going to get an output. This is the Freeman double bounce element. This is volume scattering. This is surface scattering. And if one is interested, they can generate the color composite. This is the color composite image generated from Freeman. And if one wants to compare the Freeman decomposition and Yamaguchi decomposition, so Freeman decomposition is generated with speckle underscore decomposition. Another decomposition you can do by going to the radar, go to the polarimetric matrix, again go to the polarimetric decomposition, and here I am going to select Yamaguchi decomposition. So select Yamaguchi, again window size I am going to select 1, and here in decomposition I am going to write Yamaguchi. Otherwise it will overwrite the previous file. So after changing the name Yamaguchi decomposition, I will be able to generate another product for Yamaguchi decomposition. I think yes. Source yes. Source product was selected. Actually, this error was generated because source product we had selected as the decomposed our input here, but the input should be given of the speckle filtering. Now I think it should work right now. Here I am going to give the name Yama for Yamaguchi model, and this has been selected. Now I'm going to click on run. Now the decomposition was done for the data set using Yamaguchi decomposition modeling. So here you can see again the different decomposition models, and fourth element helix scattering has also been generated here. So I'm going to just see the color composite generated by Yamaguchi decomposition model. So automatically it is selecting the double bounce scattering is represented by red color, volume scattering is represented by green color, and surface scattering is represented by blue color. One can store the RGB also. Now we are going to get this result. Now similarly one can select the if they are getting there is no noise in the data set, so they may select the option to not to do any kind of speckle filtering, and they can process the data set. So this output will be generated, and for each and every resolution cell we will have one value in double bounce scattering, in volume scattering, in surface scattering. If you want to check, you can zoom any study area, you can zoom any location, and you can see like for each and every location, like here if you will see the Yamaguchi double bounce scattering model, particularly for this location, double bounce scattering is -13, volume scattering is -15, surface scattering is -5, helix scattering is -15. It means that this area should be dominated by surface scattering, because surface scattering is very high in comparison to the other elements. Like if you see the surface scattering value is -5 only, but for double bounce scattering it is -13, for volume scattering and helix scattering it is -15. It means that this pixel or this resolution cell will be dominated by surface scattering. So when you will see the same area in the color composite image, so this will be appearing as blue color. So accordingly one can find out the information, scattering information of different objects, different features. Here one can easily see this is river channel. This could be easily seen. This is contributing in the surface scattering, because this is surface scattering image, and entire sea surface is appearing as bright object in surface scattering. It means that they are contributing in surface scattering. Now, after doing the decomposition, now people are in requirement to ortho rectify the data set. So there are two options. Either one can do the ortho rectification before processing, and another option is they can do the ortho rectification after processing the data set. And there are several other tools to classify the data set, because when you go in the raster option, so there are supervised and unsupervised classification options also. They can go and do the classification if they want to do the classification using the SAR data set. But now currently we are going to do the ortho rectification of PolSAR data set. So now we are going to do the ortho rectification. So first of all, we will have to select geometric. Then we are going for the terrain correction. In the terrain correction, we are going to get range Doppler terrain correction. Now for each and every processing step, like in the case of decomposition also, we are going to get this option help. If one is interested in exploring the help, like what type of processing is going on, which algorithm is used, so they can go, because they can go through the help of this software, because this is prepared in the very scientific approach. The references and all these things are given in very deep detail, so that a learner or a researcher can explore the different processing steps, even polarimetric modeling. Suppose I am just going to close it. I am going to open the polarimetric. If I am interested to know the polarimetric decomposition modeling approaches, so simply in the help, if you click on help, so it is going to take some time. So the help menu for polarimetric decomposition modelings will be opened here. So you can expand it. You can see that Sinclair, poly decomposition, Freeman, Yamaguchi, and there some information, brief information and detailed information, both are given, and the references are also given if one is interested to explore about for the scientific writing, or to make a good understanding of the modeling approaches. So they can go through these references. Like this is the book written by Lee and Potier, Polarimetric Radar Imagery, and another is the paper written by Dr. Ridha Tauji of IEEE. This is publication of IEEE Transaction of Geosciences and Remote Sensing. So they have given the Tauji decomposition model for target scattering decomposition in the terms of the role invariant target parameter. So they can go and explore. Similarly, if one is interested to go in detail of some other approaches, like when you are going for the terrain correction, so what is the terrain correction, how it is going to be implemented, so all the details are given and their references are also given. So one will have the complete guide related to each and every tool, and they can go and explore. Now we are going to do the terrain correction of the polarimetrically decomposed data set. So we are going for this radar option, then going to the geometric, after then terrain correction, then range Doppler terrain correction. Now in the range Doppler terrain correction, I am going to select the tool, this multi-looked speckle filter decomposed, and Yamaguchi decomposition, suppose I am going to select as input as a source product. So our output has been defined, and the terrain corrector product will have the name _TC. Now again we are going to the processing parameters. When you are going to select anyone, so it that particular product will be selected. Here I am not going to select, so that automatically it will be selected. It is going to select all. Now it will be done. The ortho rectification will be done with the help of DM, digital elevation model. So if one will have their own digital elevation model, so they can select the external DM. Now here I am interested to do the automatic download of the SRTM DM with 1 arc second. So particularly for the 30 meter, 1 arc second will be the 30-meter resolution DM. So with that one, I had shown the difference in the ortho rectification, like the positional accuracy. We had checked with 1 arc second, and like it 3 arc second also. Like we had compared to 1 arc second and the 3 arc second. So in 1 arc second it was 30 meter, 3 arc second it was 90 meter. So we had seen lot of variation was there in the terms of the positional accuracy in the data set. So here I'm going to select SRTM 1 second DM. So this will be the dimension of the output product. Approximately pixel spacing will be 14.61. And here there are several other options if one is interested to generate the local incidence angle, because this is really required to ortho rectify the data set. So to generate the actual back scatter cross section. So from here one can generate the local incidence angle image also. So selected source bands will be coming as output here. And now I am going to do the ortho rectification of the polarimetrically decomposed product. Now here I have checked, by default it is checked the mask out areas without elevation. So generally what will happen, the areas without elevation like water bodies, this will be the masked. So you are not going to get any information after doing processing. So if one is interested to keep the information for the areas or location without elevation also, so simply you will have to uncheck it. Okay, after unchecking it, again just re-verify the data, each and everything is correct. Now I am going to, you can select any resampling tackling bilinear, nearest neighbor, it depends on you. And I am going to click on a run so that the data set should be ortho rectified. Now here you can see in the background it is downloading the SRTM DEM. Okay, so to do this processing with the help of automatic download of the DM, internet connection is required. So first it will download the DM, then it will do the processing. Now here you can see this has been downloaded, and now the processing is going on to ortho rectify the data set. And like here the system is very fast, so that we are able to complete this processing in few seconds. It depends on the system, sometimes system as well as the internet speed also. So now we are going to see the output ortho rectified product. So this is the ortho rectified product. You can see now it has been ortho rectified. You can see the effect of topography here, that could be easily seen here. Okay, and now I am going to generate color composite. So this is the color composite image generated. I think there is something happened, so that 1 minute again, I think we should again try to generate. Open RGB, red and green and the blue. This is okay. Yes, the similar result we are getting. So here we are going to get a wrong type of interpretation of these values, but I don't think that these are the realistic values. Otherwise one can do the georeferencing manually also, or they can try, but here something happened so that we are going to get these values. Yes, actually visualization has been done, but in the background it is showing surface scattering. So it should be blue, but I do not know what happened. Again I think I should select it again, because scattering it is showing wrong. There is something wrong with the, yes, something is going on, and that is not correct, because Here it should be surface scattering highlighted by the red color. I think there is some problem particularly in this step after generating this one, because most of the time it is showing the correct, but currently it is not showing. But here you can check the values, particularly for this area. Surface scattering is -3, volume scattering is -23, Dow bounce scattering is -20. Means surface scattering is dominant here because it has values only -3, and remaining are having value -20. So differently, or one can generate the color composite. It might be possible that since these values are represented on at a decibel scale, so it might be possible that problem is coming due to that also. But if one is interested, they can export the data set in any other software, and they can see the values, because according to the values, this should be highlighted in red color. But here, sorry, it should be highlighted in blue color, but we are getting the red color. But anyhow, we are getting the correct values. We are not going for the visualization only. So the values are there. And if one is interested, currently in this here, I do not have Google Earth. But if one is interested to see, to overlap the image, extent of this image on the Google Earth, so simply they can right click here. They can simply click on export view as Google Earth KMZ, and they can save it at the folder. Suppose here I'm going to save here only, snap output. So one RGB will be created, sorry, color composite image of KML file of the color composite image will be generated, and one can export, and they can see on the Google Earth also. Okay, so I hope that you will be able to do the practical with the help of this tutorial. And if you are having any problem, you can discuss, because if you are getting this problem in your system also, then I would like to suggest that export the data set in any other file format, either GOT file format or any other file format. And after exporting the data set, again you can generate the color composite in the softwares. There are several softwares. Even you can generate the color composite in QGIS, you can generate in ArcGIS, you can generate in Envy, you can generate in ADAS. There are several commercial as well as the open source softwares, so you can use them. And you can generate the images according to your modeling approach. Now, I think this will be helpful for you, and thank you for attending this tutorial.